lecture series on differential equations. Today's lecture is on boundary value problems. Till now, we had learned about initial value problems, where we used to have a differential equation and some initial conditions on the unknown function and its derivatives. We call them initial conditions because we were having them at most of the time at the initial point. A similar kind of problem is also existing in the practicals, that is called the boundary value problems. So, let us see a typical example of an initial value problem. Here I had used one linear differential equation of the second order and the initial conditions as y, the function at a is y naught and function's derivative at a is y 1. Here we were having both the function and its derivative at the same point is being defined. In boundary value problem, what we used to have a differential equation. So, again I had used the same differential equation y double dash plus p x y dash plus q x y is equal to r x, that is linear differential equation of the second order, and we may have the boundary conditions which are such as a 1 y at a plus a 2 y dash at a is equal to 0 and b 1 y at b plus b 2 y dash at b is equal to 0, where certainly my this a 1 a 2 and b 1 b 2 they should not be all 0. That is, in this also both a 1 a 2 should not be 0, here also both b 1 b 2 should not be 0. We see here the difference between these two. The differential equation is the same. Here we were having the condition only at a point a, and here we are having the condition at a point a as well as at a point b, and both are involving our function as well as derivatives. Now, these points a and b are typically the points on interval where this equation is defined. So, the end points a and b, that is what we are calling them boundary value problems, that is the conditions are given at the boundary points. Thus, what we are saying that the value of dependent variable y or its derivative is specified at two different points. We can simplify our boundary conditions more. Say for example, here I have one simplified boundary condition where the unknown function is specified at two different points only. You see that y at a is y naught and y at b is y 1. Here we are not having any function derivative as they were in this original boundary conditions. Now, if I see the two problems, the initial value problem, this one where the conditions are specified at a single point of the function and a derivative of the function, and this boundary value problem where the differential equation is same, but the condition is defined at two different points. They are looking similar. Now, what do we have read about the initial value problem? That and with the we are just getting a formal definition of 2-point boundary value problem. A differential equation together with suitable boundary conditions form a 2-point boundary value problem. That we are just getting is that why the name is boundary value problem. And a typical example, again I am repeating the same example here, that y double dash plus p x y dash plus q x y is equal to r x with boundary conditions at two specified points a and b, y at a is y naught and y at b is y 1. So, this is one simple example. Now, let us move with this typical example of ours and try to learn some more terms in this problem. The differential equation, if we see in this boundary value problem, we do certainly recognize that this is second order linear differential equation, because we are having is our unknown function and its derivative, they are occurring separately, and this p x and q x are the function of x and r x is also a function of x. So, this is second order linear differential equation where R x is not 0, it is non-homogeneous, otherwise if 0 then it is homogeneous. This is linear. So, we would call with these two boundary conditions, y at A is y naught and y at B is equal to y 1. So, now this differential equation with these two boundary conditions will be termed as linear boundary value problem. This is being mainly classified into two forms. One is homogeneous. In homogeneous, what we will have, as the differential equation would be homogeneous, that is my R x would be 0. That says my differential equation would be y double dash plus p x y dash plus q x y is equal to 0. Moreover, you see here that our boundary values are also, that is boundary conditions are also changing, that is y at A is 0 and y at B is 0. This is homogeneous one, and otherwise it is called non-homogeneous. So, we will take this typical example. Here even if R x is 0, but if y naught and y 1 are not 0, we will call them non-homogeneous, or if R x is not 0 and y naught and y 1 are 0, still it would be called non-homogeneous one. So, this is one classification of linear boundary value problems. We had seen that in our initial value problem, if I was having this kind of equation, of course, we are talking about linear equations, and if we had this initial conditions at A of the function y and its derivative at A, we do know that under the assumption of this function's coefficients p x and q x and r x being continuous, we had that this initial value problem was having a unique solution. Now, you see our boundary value problem. Our boundary value problem is having the same differential equation, but the boundary conditions, that is y at A is y naught and y at B is equal to y 1. Now, if I make the same assumption, that is my coefficient p x, q x and r x, they are continuous, we cannot guarantee whether the solution may exist or solution will exist for this problem or not. And if the solution does exist, still we cannot guarantee about the unique solution. These things that says is for under similar assumptions of p x, q x and r x being continuous on the interval a b, this boundary value problem may or may not have solutions, and if it has solutions, it may have one or many solutions. We will understand this or see with help of certain examples first, and then we will go for the concepts. So, let us see some example. First example, solve the boundary value problem y double dash plus 3 y is equal to 0, conditions y at 0 is 1 and y at pi is equal to 0. We see this is non-homogeneous boundary value problem, since my boundary conditions are not 0. Solution. We see that our differential equation y double dash plus 3 y is equal to 0. This is homogeneous linear differential equation of second order. We do remember how to solve it. So, we get the characteristic equation as lambda square plus 3 is equal to 0. Its roots is of course plus minus square root 3 I, that is the complex conjugate roots. So, in that case we do know that our general solution will be of the form C1 cos square root 3 x plus C2 sin square root 3 x. This is the general solution of this differential equation. Now, we have to get the solution of this boundary value problem, that is we have to get a solution y such that these conditions are also satisfied. So, let us see in this general solution, if I use these conditions what we would get. So, satisfy the boundary conditions that y at 0 is 1 and y at pi is 0. So, if I put in our solution x is equal to 0, we would get C1 cos 0 plus C2 sin 0. This implies that C1 is 1, and if now I put x as pi, I would get as C1 cos square root 3 pi plus C2 sin square root 3 pi. This should be 0. Now, since we already have in the first equation that C1 is equal to 1, this will give me that C2 is equal to minus cot square root 3 pi. Thus, we have got a solution of these, that boundary value conditions have given me two values of C1 and C2, C1 as 1 and C2 as minus cot square root 3 pi. So, we have got the solution yx as cos square root 3x minus cot square root 3 pi sin root 3x. Since we have got a single solution, we have got that this boundary value problem has a unique solution. This is of course a case of non-homogeneous linear boundary value problem with unique solution. Let us have one more example. Solve the boundary value problem y double dash plus y is equal to 0, y at 0 is 1 and y at pi is equal to d. We see that from the previous example we have differed only in the differential equation, as the coefficient of y has been changed from 3 to 1, but we have changed our boundary condition, only the second boundary condition. There we had used y at pi is equal to 0, here I am using y at pi is equal to d. Now, let us see what is the solution of this. The given differential equation is y double dash plus y is equal to 0. We see again that this is linear differential equation. So, its characteristic equation would be lambda square plus 1 is equal to 0, and we will get again the complex conjugate characteristic roots, that is plus minus I. So, the general solution would be of the form C1 cos x plus C2 sin x. Now, see with this boundary condition, this is the general solution. Now, try to satisfy the boundary conditions. So, put x is equal to 0 in this general solution, we would get that y at 0 we would get as C1 and that is given as 1. So, we have got from the first condition C1 as 1. When I put x is equal to pi here in this solution, we get y at pi is equal to C1 cos pi plus C2 sin pi, and the given condition says is it should be equal to d. What it gives me, that is, it gives me that is, since C1 is already 1, cos pi is minus 1, I would be getting it, and sin pi is 0, I would be getting it C1 is equal to minus d. Thus, what we have got, that both the boundary conditions are giving me the value of C1 only. The first condition is giving me C1 is equal to 1, the second condition is giving me C1 is equal to minus d. Now, if this d is equal to minus 1, then certainly I do get the solution as C1 is equal to 1. So, let us see, if d is equal to minus 1, then I get C1 is equal to 1 and C2 any constant. So, what will be the solution of my boundary value problem? I would get infinite many solutions as cos x plus C2 sin x, where C2 is the arbitrary value. Now, if d is not minus 1, what I would be getting? C1 is equal to 1 and C2 is equal to minus d, and since d is any value other than minus 1, I am getting two different values for C1, that says the boundary conditions are not compatible on C1. What it says is there is no solution for this boundary value problem. So, now we had seen in this example that if we do have the boundary condition, where I had actually taken an example, a general one, the condition a general constant d, and we have got that if I give a particular value to that d as minus 1, we are getting infinite many solutions, and if it is not minus 1, we are getting no solution. So, now we have got the examples, that is under the same condition. If you see my differential equation, the coefficients are continuous functions, the boundary conditions are simple one, but what we are having is, that is, this may have many solutions or may not have solution depending upon d. Now, let us see what we had learned about this non-homogeneous. Both the examples we have taken of non-homogeneous linear boundary value problems. Now, let us go back to, that is, before actually solving this boundary value problem, we will see is, that is, how we have done this initial value problems, because our differential equation is same, only the conditions have changed. We remember that if we are having this non-homogeneous linear differential equation, Corresponding to that, we always had a homogeneous linear differential equation, and the solution of non-homogeneous linear differential equation had come through the solution of homogeneous linear differential equation, and the same thing was true for the initial value problem as well. And there we have got that if we are using initial value problem, we are getting a unique solution. Here we are getting is that is in non-homogeneous linear differential boundary value problems, we have got that is either we are not having a solution, or we are having a unique solution, or we may have many solutions. Let us see what corresponding to that, can we have a homogeneous boundary value problem? Certainly we can have. So, if my non-homogeneous boundary value problem, again I am taking that simple example of where this my boundary conditions are only at 2 points. So, if I do have this boundary value problem where I do have simple linear differential equation of the second order non-homogeneous, and the conditions where y naught and y 1 are not necessarily 0, or rather we can take, we are taking them non-zero, then the corresponding homogeneous boundary value problem would be when r x is 0, that is it is same as that linear differential equation, that is I am having is homogeneous linear differential equation. Moreover, I do require that the conditions also must be 0. If you do remember, in initial value problem we had never discussed about the conditions, initial condition. We have just discussed about the differential equation, that is non-homogeneous, correspondingly that we had homogeneous linear differential equation, we got the general solution from here, then we got general solution of non-homogeneous one, and then we satisfied the initial value. Now, here what we are saying is that is homogeneous boundary value problem says is we are homogenizing, or we are making this y naught and y 1, that is the conditions for boundary value, them also as 0. So, this is the corresponding homogeneous boundary value problem. In initial value problems, we had got that the solution we are getting through homogeneous one. Let us see, is there any insight, that is if I try to solve this homogeneous boundary value problem, can I get something, or can I assured of any solution, and if that is happening, can I relate it with this non-homogeneous? Let us try to say it, we do not know exactly at this moment. What we are observing here, one thing is that if I put y is equal to 0, then this will satisfy this equation as well, the initial this boundary conditions. So, this y is equal to 0 for all x, this will satisfy this boundary value problem, and certainly this would be a solution. This solution what we will call trivial solution, and of course, we are not interested in this trivial solution, because it is not giving me anything, or it is not giving us any insight about this differential equation. So, we are certainly interested in non-trivial solution, that is solution other than 0 value. Let us see some homogeneous boundary value problems and their solution with the help of example. So, again I am having this example, y double dash plus 3 y is equal to 0, y at 0 is 0 and y at pi is equal to 0. If we see, this is corresponding to our first example, a homogeneous boundary value problem. In the first example, we had the same equation, but the conditions were here different, that is they were not 0. Now, let us see the solution of this. We had seen the general solution of this differential equation was C1 cos square root 3x plus C2 sin square root 3x. Now, try to satisfy these boundary values. So, if I put x is equal to 0, I would get C1 as 0. Now, if I put x is equal to pi, I would get y pi is equal to C1 cos square root 3 pi plus C2 sin square root 3 pi, but since C1 is 0, so I would get only C2 sin square root 3 pi is equal to 0. Now, since sin square root 3 pi is not 0, this simply gives me C2 is equal to 0. So, what we are getting is both C1 and C2 0, that says I am getting the trivial solution only 0. So, now let us see the another example. This homogeneous boundary value problem corresponding to the other example. Do you remember the other example we had y double dash plus y is equal to 0. Here I had put the boundary conditions also at 0. So, we are having y at 0 is 0 and y at pi is equal to 0. Solution, we do remember that the corresponding to this differential equation, the general solution was C1 cos x plus C2 sin x. Now, try to satisfy these boundary conditions. So, at x is equal to 0, I would get C1 is equal to 0 and at x is equal to pi, I would get C2, that is C1 sin pi cos pi, and since C1 is 0, I would get only C2 sin pi, and since sin pi is 0, I would get C2 any constant. So, what we are getting the solution? We are getting the solution that these boundary conditions are giving me C1 as 0 and C2 any arbitrary value. Thus, we get the solution of this boundary value problem as infinite many solutions C2 sin x, infinite many because C2 is any arbitrary constant. Now, in these examples we had seen that our differential equation, that because we are coming with the homogeneous boundary value problems. So, our and both the times our boundary values remained 0 and pi. So, our boundary conditions remained same. The only thing what we have changed was our differential equation. In the first example, I had y double dash plus 3y here, and here I am having is y double dash plus y, that is the coefficient of y has changed. And in the first example, we had got that boundary value problem was having a unique solution, and this boundary value problem is in the first example we got that the boundary value problem was not having any non-trivial solution, and in this one we are having a non-trivial solution, rather infinite many solutions. Now, let us see this same problem, that is where I am changing only because boundary conditions are not changing, my boundary values are not changing. So, only thing which is changing is in this equation, and in this equation also the thing which is changing is only the coefficient of y. So, let us try to see this particular problems, or rather we could say is that now for solving boundary value problems we are first trying with very special kind of problems, and those special kind of problems now we would call them as eigenvalue problems also. Let us see what these we are saying. We do have a differential equation of the form y double dash plus lambda y is equal to 0, and the boundary conditions y at 0 is 0 and y at pi is equal to 0. Now, we had already seen that in our examples we had the different values of lambda. When I had lambda is equal to and 1. When I had this lambda is equal to 3, we have got trivial solution only. When lambda is equal to 1, we have got infinite many solutions. So, what we are gaining is that because of this lambda, that is this value of lambda is changing, and we are getting either a solution or you could say only trivial solution, because here no solution will not be a question, because we will always get the trivial solution. Trivial solution we will keep in the category of no solution. So, what we are getting is because of this value of lambda we may get trivial solution or non-trivial solution. So, now we are going to define the terms. The values of lambda for which non-trivial solution exists for boundary value problem are called eigenvalue, and the solution corresponding to them are called eigenfunction. So, what we have got? We have seen that lambda is equal to 3, for this will not be an eigenvalue because we are getting only trivial solution, and what we call eigenvalue if it is non-trivial solution is existing. So, lambda is equal to 1, since non-trivial solution is existing, that would be called an eigenvalue, and corresponding solution, what was the solution if I do remember? That was C2 sin x. So, that is the corresponding eigenfunction. So, now this problem we would call eigenvalue problem. what we are having is, again I am summarizing the things, y double dash plus lambda y is equal to 0, y at 0 is 0 and y at pi is equal to 0. Lambda is equal to 1 is an eigenvalue and the corresponding eigenfunction is C2 sin x. Lambda is equal to 3 is not an eigenvalue. Now, let us have something that is more general. Here we have just seen two typical examples. Can we find out all the lambda values for which the non-trivial solution does exist? Let us see if we could do it. So, to find eigenvalues and eigenfunction of this boundary value problem, y double dash plus lambda y is equal to 0, y at 0 is 0 and y at pi is equal to 0. Since in our examples we had seen the different values of lambda are giving me, that is either solution is existing or there is no solution, that says is this is depending on the value of lambda. Now, lambda is any real number. Let us divide into 3 cases it. What are the 3 cases? Positive lambda, lambda 0 and negative lambda, because that would give me actually my general solution of this differential equation as different. Let us discuss these cases one by one. Let us take the first case. Case 1, lambda positive value. So, suppose lambda is mu square. Then the given differential equation y double dash plus lambda y is equal to 0 will become mu the y double dash plus mu square y is equal to 0. Now, what will be its characteristic equation? That should be m square plus mu square is equal to 0 and will give me the two complex conjugate characteristic roots, that is plus minus mu I. Thus, we would get the general solution of the form C1 cos mu x plus C2 sin mu x. Now, you see that is why I have taken lambda is equal to mu square, otherwise I have to write here square root lambda. And we will assume here that mu is positive, because it does not matter whether mu is negative or positive, lambda will always be mu square, that is a positive real number. So, we will take mu as positive. Now, the boundary conditions, that y at 0 is equal to 0 and y at pi is 0 would give me that C1 is 0, the first condition, when x is equal to 0, when x is equal to pi, we will get y pi as C2 sin mu pi is equal to 0, because C1 is already 0. Now, for getting non-trivial solution, I must get that C2 should not be 0. That says is that I must get sin mu pi is equal to 0. We do know that it will be 0 if mu pi is equal to n pi. That says is mu must be a positive integer. That is why you do understand that why I have taken mu to be positive. Now, what we have got from here, that I will get non-trivial solution for this differential equation or this boundary value problem if my the value lambda is equal to mu square and mu is a positive integer. That says is the eigenvalues or the lambda should be 1, 4, 9 and so on, like n is square, because n is a positive integer. So, these would be, so my eigenvalues for the problem would be 1, 4, 9 and n square, in general n is square, and the corresponding eigenfunctions would be c times sin nx. Thus, we would be getting is C2 is, that is any non-zero value, that is arbitrary value. So, we would have c sin nx for n is equal to 1 to 3. So, I would be getting is my eigenvalue as n square and corresponding eigenfunction as c sin nx. So, lambda positive 1, 4, 9 and n square, like that, they are eigenvalues. Now, you see is that lambda is equal to 3 is not coming over here, and so we have got that it was not an eigenvalue. Now, let us see the second case, lambda is equal to 0. In this case, our given differential equation, what it will become? Y double dash is equal to 0. that is we would be having two characteristic roots 0 and 0, that is equal correct, and in that case we do know that our general solution will be of the form C 1 plus C 2 x. Now, if I try this boundary conditions for this, at x is equal to 0 I will get C 1 is equal to 0, at x is equal to pi I would get C 1 plus C 2 pi is equal to 0, C 1 is already 0, pi is not 0, gives me C 2 is equal to 0, that is at lambda is equal to 0, the boundary conditions are providing me only the trivial solution where both C 1 and C 2 are 0. So, we get only trivial solution, thus lambda is equal to 0 is not an eigenvalue. Now, let us come to the third case, and lambda is negative. So, let us assume lambda is equal to minus mu square, where mu square of course would be positive, because we are taking mu to be a positive real number. Now, then what will our differential equation become? Y double dash plus lambda y is equal to 0. It will become y double dash minus mu square y is equal to 0. So, what will be its characteristic equations? M square minus mu square is equal to 0, that says I would get characteristic roots, two different values mu and minus mu. Thus, my general solution would be of the form C 1 e to the power mu x plus C 2 e to the power minus mu x. Now, here if I try to find out with the boundary conditions, whether boundary conditions what they are giving, they would give me if at x is equal to 0, we would get C 1 plus C 2 is equal to 0. At x is equal to pi, we would get C 1 e to the power mu pi plus C 2 e to the power minus mu pi is equal to 0. Now, this first condition, that C 1 plus C 2 is equal to 0, gives me that C 1 is equal to minus C 2 or C 2 is equal to minus C 1. So, let us take it C 1 to be C, then C 2 is minus C. Now, substitute this in the second equation, what it gives me, that C times e to the power mu pi minus e to the power minus mu pi is equal to 0. Now, we do know that e to the power mu pi minus e to the power minus mu pi, this does not have, or this will not be 0 for C real, that says is again we are getting only trivial solution, that says that C 1 and C 2 should be 0, and so no negative eigenvalues as well. So, now what we had learned, that now generalize this problem and its findings. What we had learned, the boundary value problem, y double dash plus lambda y is equal to 0, y at 0 is 0 and y at L is equal to 0. Now, what we had got there, my condition was y at pi. Now, I am not working with the interval 0 pi only, we are generalizing it to 0 to L. If I generalize it, what we would get, that it will have eigenvalues only as of n square pi square upon L square. What we are doing is, that is we are, now you can do this as an exercise for yourself, that is rather than putting the boundary value boundary condition y at pi is equal to 0, put y at L is equal to 0 and try to satisfy it, you would get that the lambda value for the lambda you would get is n square upon pi, n square into pi square upon L square, for n being a positive integer 1, 2, 3 and so on. And the corresponding eigen functions would be c times sine n pi x over L for n is equal to 1, 2, 3 and so on. That is, if eigenvalue is n square pi square upon L square, its eigen function is c sine n pi x over L. That is, we would have infinite many solutions corresponding to this eigen value. This is what we have got generally, that is this kind of problem what we are having is eigen values and eigen function of this kind of boundary value problem. Let us see one example here. Find the eigenvalues and corresponding eigenfunction of the boundary value problem y double dash plus lambda y is equal to 0, the conditions are, now you see, y at 0 is 0 and the second condition is y dash at 1 plus y at 1 is equal to 0. Till now what we had seen, my differential equation is same. We are having homogeneous boundary value problem, but my boundary conditions are now not that simple boundary condition that at 2 points the value of the function. Now, we are involving the derivative as well. Let us see, try to find out the eigenvalues and eigenfunction of this example as well, or this particular. Again we see the differential equation is y double dash plus lambda y is equal to 0. We will again see with the cases, because this value of the lambda would be making our general solution differently. So, again we will take those 3 cases, that lambda is 0, lambda positive and lambda negative. Discuss these 3 cases one by one. First, the case lambda is equal to 0. In this case, our differential equation will become y double dash is equal to 0, as we had already seen. The general solution in this case would be C 1 plus C 2 x. Now, our boundary conditions involve y dash also. So, let us see the 2 boundary condition, y at 0 is 0 and y dash at 1 plus y at 1 is equal to 0. If I put x is equal to 0, I would get C 1 is equal to 0. And the second condition says is y dash at 1. What will be y dash x? It would be simply C 2, that is C 2, and y at 1 would be C 1 plus C 2. So, we are getting C 1 plus twice C 2 is equal to 0. Since C 1 is already 0 from the first condition, the second condition would give me C 2 is 0. That is, again we are getting the trivial solution of these equations. C 1 is 0 and C 2 is 0. That says is I would get only trivial solution y as 0. So, lambda is equal to 0 is not an eigenvalue for this problem. Now, come to the case 2, lambda as positive value. Again let lambda as mu square and we will again take mu to be positive real number. The given differential equation will become y double dash plus mu square y is equal to 0. We had already seen that the general solution in this case is of the form C 1 cos mu x plus C 2 sin mu x. Now, put the boundary conditions. So, for boundary conditions require y dash also. So, first calculate y dash x, that would be minus mu C 1 sin mu x plus mu C 2 sin cos mu x. Now, y at 0 is 0, that is, if I put x is equal to 0 in the first general solution, I would get C 1 is equal to 0. Then when I am putting y at 1, here what I would get? C 1 cos mu plus C 2 sin mu. When I put y dash at 1, I would get minus mu C 1 sin mu plus mu C 2 cos mu, and this is given is equal to 0. Now, simplify it, what we are getting is C 2 sin mu plus C 2 mu cos mu is 0, or more simplified form C 2 times sin mu plus mu cos mu is equal to 0, because the term C 1 is 0. So, the term containing C 1 we had eliminated over here, and from here we will get non-trivial solution, that is non-trivial solution, that means I require C 2 to be not 0. That says is my this coefficient of C 2, that is sin mu plus mu cos mu, this should be 0. And that is what is being writing here, that is for C 2 not to be 0 implies that sin mu plus mu cos mu should be 0. So, what we are getting is, now I am replacing mu with square root lambda. We are saying is lambda is an eigenvalue only if it satisfies this equation. What is that equation? Sin root lambda plus root lambda times cos root lambda is equal to 0. That is, all lambda which are satisfying this equation, they would be the eigenvalues for our boundary value problem, where my differential equation was y double dash plus lambda y is equal to 0, but the boundary conditions have changed. So, you see that if boundary conditions are changing, our eigenvalues are changing, and lambda has to be positive. So, we do get lambda positive, and satisfying this equation would form the eigenvalues of lambda. Now, how to find out this one? Of course, this is not a simple equation which we can solve directly. There are numerical methods, that is, we put certain values for the lambda and then we get, that is, what are those particular values. So, which can be obtained by numerical methods. Of course, corresponding eigenfunction would be, so suppose lambda 1, lambda 2, that is, those are which are satisfying this equation, there would be of course certainly more than one values, they are eigenvalues. Then the corresponding eigenfunctions are k n sin square root lambda n x for n is equal to 1, 2, 3. So, now this n we are using as the different values of the lambda for which this equation is satisfied. We are naming them as lambda 1, lambda 2, lambda n. In this eigenfunctions, k n is arbitrary, that is, corresponding to each eigenvalue we would get infinite many solutions, and we are calling them eigenfunctions. Now, discuss the third case when lambda is negative. So, let us again suppose in the similar manner that lambda is equal to minus mu square and mu is a positive real number. The given differential equation will become y double dash minus mu square y is equal to 0. As we already know that in this case the general solution would be of the form c 1 e to the power mu x plus c 2 e to the power minus mu x. Now, what will be this y dash? Mu times c 1 e to the power mu x minus mu times c 2 e to the power minus mu x, or in more simplified manner mu times c 1 e to the power mu x minus c 2 e to the power minus mu x. Now, boundary conditions would give me y at 0 is 0, that is, c 1 plus c 2 is equal to 0 or c 2 is equal to minus c 1, and y at 1 and y dash at 1 we would get mu c 1 e to the power mu minus mu c 2 e to the power minus mu plus c 1 e to the power mu plus c 2 e to the power minus mu is equal to 0, which we simplify when we would get c 1 times 1 plus mu e to the power mu plus c 2 times 1 minus mu e to the power minus mu is equal to 0. If we try to solve this equation, that is c 2 is equal to minus c 1, if I put, I would get c 1 as 1 plus c 1 into 1 plus mu times e to the power minus mu minus 1 minus mu e to the power minus mu is equal to 0. For getting non-trivial solution, I must get c 1 to be non-zero, and that says is I should get the coefficient of c 1 as 0, or rather we should get 1 plus mu e to the power mu minus 1 minus mu e to the power minus mu is equal to 0. But this equation does not have a solution which, or this equation does not give me any solution. So, what we are getting is we cannot get non-trivial solution in this case also. So, with the differential equation now we have got that lambda is equal to 0 is not an eigenvalue, lambda negative is not an eigenvalue. The only thing lambda positive and satisfying one particular condition or one particular equation, they are eigenvalues, and the corresponding eigenfunctions also we had seen. Now, we had seen this eigenvalue and eigenproblem. This was a very particular kind of differential equation we have discussed, y double dash plus lambda y is equal to 0, and we have discussed the particular boundary conditions also. We had little bit variated our boundary condition. Now, we will discuss one more practical problem, or that is the problem which is arising in many applications. The name is associated with Strum and Lowry, and thus we would be calling them Strum-Lowry boundary value problems. Let us first define what this problem is. A Strum-Lowry problem consists of a differential equation. This is of a special form. P x y dash its whole derivative plus q x plus lambda r x times y is equal to 0. That is the equation of this form. If any differential equation we are getting, this is second order differential equation, certainly it is going to be linear, and if it can be written in this form and the boundary condition, this equation must be defined on an interval a to b, and together with the boundary condition at the end points a and b as a1 y a plus a2 y dash a is equal to 0, b1 y b plus b2 y dash b is equal to 0. Now, we see the system Lowry problem, our differential equation is linear homogeneous, the boundary conditions they are linear and homogeneous. So, this is actually a linear homogeneous boundary value problem, where the equation is of a special form. In this Sturm Lowry problem, we do require for this boundary conditions that both a1 a2 and b1 b2 simultaneously should not be 0. This differential equation I dash its whole derivative plus q x plus lambda times r x y is equal to 0. This is known as Sturm Lowry equation. So, the Sturm Lowry boundary value problem is basically about this equation and the general boundary linear boundary conditions. If do you remember the Legendre equation, 1 minus x square y double dash minus 2 x y dash plus n into n plus 1 y is equal to 0. You had already solved this equation. You see that we can rewrite this equation as 1 minus x square y dash its whole derivative plus n into n plus 1 y is equal to 0. Now, you see here, if I compare it with this Sturm Lowry equation, I get p x as 1 minus x square, q x as 0 and lambda as n into n plus 1 and r x as 1. Then we do know that Legendre equation is also a Sturm Lowry equation. Similarly, actually you do see is that is boundary this Bessel's equation which you had already done in the series solution, that is also a Sturm Lowry equation, but that requires a little bit calculation. So, let us see. I am writing this Bessel equation in y and t. So, t square y double dash plus t y dash plus t square minus n square times y is equal to 0. This is the Bessel's equation. Let us change the variable t with k x. That says is my y dash and y double dash would also get it changed. So, dy over dt I would be, that is here y dash and y double dash were with respect to the function with the variable t. So, dy over dt would be 1 upon k dy over dx, d2y over dt2 would be 1 upon k square d2y over dx2. If I substitute this in this given Bessel equation, I get x square d2y over dx2 plus x times dy over dx plus k square x square minus n square times y is equal to 0. We see that this is an equation in y and x. Now, divide this equation by x. So, what we get x times d2y over dx2 plus dy over dx plus k times x minus n square upon x into y is equal to 0. Now, rewrite this in the form of Sturm Lowry equation. So, I do get x times y dash its derivative plus minus n square upon x plus k x into y is equal to 0. Now, if I compare with this p x, q x and lambda, we will get p is equal to x, q x as minus n square upon x and r x as x, and of course, lambda is here k. Then this is also Sturm Lowry equation. Now, if you do remember, we have done in this whole lecture one special equation y double dash plus lambda y is equal to 0. If you see, that is also we could write as a Sturm Lowry equation and that you can check with as an exercise. With this, today I am finishing up our today's lecture of boundary value problem, where I have defined you one special problem, Sturm-Liouville problem. Now, in the next lecture actually we will discuss little bit about the properties of this Sturm-Liouville problem and how to get the solution of this particular problem. So, today we had learned boundary value problems, and we had learned that they are very different from the initial value problems. It is not necessary that we have not done the general case, we have done very special kind of equations, and we had done that special kind of equation was turning out to be one of very practical appearing problem, that is Sturm-Liouville problem, and with that I would be ending today's lecture. Thank you.